Okay, let's start this presentation. My name is Boris Lublinsky. I'm principal architect in Lightbend, mostly focusing on streaming applications, machine learning, model serving, and all the things around it. So why stream processing? The key element that everybody is looking for right now is that we process data not afterwards, but while it is in motion. Um, if you've seen the great presentation today by Yaron, who was talking about Cubeflow, he was telling that the main achievements that they've made is they replaced batch processing with the immediate processing of fraud immediately as the transaction goes through the database, and this allowed them to reduce processing time from 40 minutes to about 12 seconds. Stream processing, he was giving example of fraud detection, but the same approach is often used in cross-selling and predictive maintenance. Why machine learning? Because machine learning allows you to automatically build the algorithm for processing data. You have two options. Either you write the code manually and maintain it for the rest of your natural life, putting updates every day, every week, whatever is necessary, or you automate the process to allow machine learning to build the new models based on the existing data and thus update your algorithm much easier. It's also quite fast because once your machine learning application is in place, processing the new data takes very limited amount of time. It's more or less accurate as long as you have the accurate data, because it will build the model based on your data. I always emphasize that your model is only as good as your data is. So be very careful. If you have a good data, machine learning is great. If your data is bad, then machine learning doesn't work. And it scales because it allows you to solve the problems that otherwise virtually impossible to solve. So machine learning in stream processing is an interesting proposition that people started thinking about in the last 2 or 3 years. And it has its own quirks, because now you have to integrate machine learning itself, which is mostly the domain of the data scientist, with the stream processing, where data scientists rarely have a hand, and mostly all the work on the stream processing is done by the engineers. And for some or other reasons, these two groups don't really work too well together. So using of machine learning models in the streaming application present a certain amount of challenges. So what is model serving? In a very simple terms, it's a function that transforms incoming data in the result of that is defined by the model. There are multiple model serving approaches. The original one was embedded model, and there the model, the way it was created by data scientists, was attempted to be used in the model serving, and it never really worked too well because data scientists, I mean, no offense, but typically they don't write very performant and very reliable code. So as an alternative, there is another approach, which is model as data, which today is one of the prevalent approaches. And there are many approaches to do this, including PMML, PFA, TensorFlow exports, MXNet exports. There is a lot of ways of approaching this problem. And there are also two completely different deployment strategies for model serving. You can either use a local deployment where the actual model serving becomes part of your streaming code, or you can use a model as a service, deploy it separately, and use, for example, REST or gRPC to access the model. We will look at both approaches later in the presentation. So if we compare the two approaches, then embedding has typically maximum performance and it has the simplest infrastructure because effectively there are no moving parts. The only thing that you have to deal with is your streaming application. As a disadvantage, if you are using this approach, then the model has to be repeated in every application that is trying to use it. Changes in the code are often required when the model type changes. This typically also true for the model serving as a service approach, because if you change the model significantly, then the API is changing and you will have to do the code changes. But typically, in the case of embedding, these changes are by far more invasive. And all deployment strategies, for example, blue-green deployment, etc., have to be explicitly implemented in your streaming code, which sounds bad, but not so bad in reality, because for a lot of streaming applications, the same problem exists and they've been solved as part of the streaming applications. So model serving as a service simplifies integration with other technologies and organizational processes, because very often what is happening is streaming application is owned by one department, while model creation and model serving is used by other department. In this case, integration becomes by far easier approach compared to embedding. Once you deploy the model serving, you can reuse it between multiple applications, kind of, because in reality, if you start adding more and more application that is using the same server, you have to start scaling it, and this becomes not always a trivial proposition. It also allows to bring model serving to low power device, for example, phones, incapable of running complex models. So this becomes very important, because if your application that wants to use model serving is running on the phone and your model is large enough, that's probably the only approach that is available to you. A lot of model serving services, for example, Seldon, that we're going to talk about in the next slide, provides a lot of additional functionality besides model serving that you can easily leverage. Otherwise, you will have to build it yourself. On the disadvantages, obviously the performance is worse because for every model serving, you have to do an additional hop. There is tight temporal coupling to the model server that can impact your streaming application SLAs. And we already talked about scaling, which becomes non-trivial because it's under the purview of two different organizations. So with all this said, model serving as a service is still a prevalent approach today, and I just was trying to summarize some of the existing model servers and their pros and cons. I mean, the simplest one are single purpose ones, let's call them that way. They are not really single purpose, but they're single model purpose. And those are TensorFlow serving, PyTorch serving, XGBoost serving. They all work only for the single model type, but they provide the simplest infrastructure. One of the throughputs, one of the breakthroughs was Seldon, which is providing optimized Docker containers for popular libraries such as TensorFlow, XGBoost, H2O, MXNet, etc. But it also allows scientists to use language wrappers if their model is unique enough. It also treats model serving not as a single function, but rather as a graph. And it allows you to define the graph with additional processing units. For example, pre-transformation of the data, post-transformation of the data, and so on. It also provides support for monitoring metrics and auditable request logs, advanced deployment technologies, techniques such as Canary, Blue-Green, and one of the most important things is support for advanced machine learning insights, for example, explainers, outlier detections, adversarial attack detectors, and so on. And also, I've noticed that there were already two presentations about Kubeflow. Today, Kubeflow introduced another serving approach, which is KF serving, which you can effectively call as a serverless implementation of Seldon. So what it does is, behind the scenes, it does auto-scaling for you, so that you don't have to scale your Seldon deployment, for example, manually. It also has a lot of other interesting features. Most importantly, they are now championing the work for standardizing data plane. And again, we'll talk a little bit about it further in the presentation. So when you decide which approach, embedded versus model as a server, to use, you need to consider how the application interact with the models. And the most immediate concern is determining how you want to integrate the model into your application. Should it be embedded, or should it use other systems to access it? And this slide basically outlines some of the considerations that you need to think about. And there was another thing that is also very important. The problem with model serving is that the model changes. It would be much easier if you could deal with the model the same way that you are dealing with all other software. You create it once and then deploy it and then pray that it works correctly. With model serving, this typically doesn't work because the data is changing, your knowledge is changing. Data scientists are trying to create new, better models. So you basically have to update the model all the time. And this pattern, the streaming system pattern, allowing to update the model without interruption, is called dynamically controlled stream. And surprisingly enough, it works for both embedded model, where what you update is the model itself, and it also work for model as a service approach, because in this case, what you have to update is the URL to the newly deployed model. So that is the bit about model serving, and everybody knows how to build the models today. Everybody knows how to deploy model servers. There is tons of implementations and documentations and best practices. But when it comes to stream processing, all bets are typically off. This is the state of the art kind of today, where you are typically using Kafka, or for this purpose, I'm using Kafka here, but it can be Pulsar, it could be any log-based systems, as a main data plane, and then you build a lot of microservices that are hanging off of this data plane. The problem with this is typically the focus of the implementation is on plumbing rather than on business logic. It's very difficult to manage, provision, and deploy, and infrastructure is looking quite ugly. Believe me, I've seen quite a few implementations, and the one on this picture is one of the better ones. So what's the alternative? There is an open source project which is called Cloudflow, which allows you to boost the development productivity by allowing you to focus only on core business logic, and all the boilerplate, serialization, port configuration, operational parameters, and so on is implemented for you. The supported runtimes include Akka streams. I work for Lightbend, and we are the initiators of this project. So everything that Lightbend is doing should support Akka. It also supports Flink and Spark structured streaming. It also provides capabilities for local execution so that you can test before you deploy. It provides automated deployment, monitoring, and management. And we will look at how to do all this. But before we switch to this, if you're interested, you can go to the project page. It's completely open source project. We initiated and we maintain this project, but you are free to browse it. You are free to download the code. and you're free to experiment with this, and we'll try to support you as much as we can. So back to our slides. Cloudflow is supporting both Scala and Java APIs. Again, Lightbend is the company behind Scala, so pretty much everything that we do has to support Scala, but we also consider that there is a lot of people that either don't like or didn't have time to switch to Scala, so we support Java as well. And it provides the Kubernetes operator to work with Kubernetes. So Kubernetes is the main deployment platform for Cloudflow. We tried it on virtually any provider's platforms. I will give you an example that running on Google Cloud, but it doesn't mean that you can't, for example, deploy it on EKS or on Microsoft Cloud. So the implementation of the streams in Cloudflow is centered around the notion of Streamlit. You can think about Streamlit as a streaming microservice. And as every self-respected microservice, it has inputs and outputs. And inputs and outputs define the shape of the streamlet. You will see the shape in the code. So I wanted to explain a little bit what it really means. So the shape basically defines all the inputs and outputs of the streamlets. And currently, Streamlit can be implemented using either Spark structured streaming or Akka streams or Flink. Sorry, no support for Python yet, but we are looking for the volunteers to help us work with Python. So once you have Streamlets, Cloudflow has the definition of the blueprint, and the blueprint is effectively an execution graph that you specify to connect streamlets to each other. So the overall implementation becomes very logical and very straightforward. You define the microservices and you define the connectivity between these microservices. There is one notable thing that I didn't mention before. Every input and output of Streamlit is defined by schema. So it effectively defines strongly typed streaming connectivity between the streamlets, which allows us to validate connectivity before you deploy it, which in turn saves you enormous amount of time in debugging and testing, because we guarantee that if you define Streamlit A to produce schema A and Streamlit B to consume schema A, they are compatible. If the schemas are different, we won't build the application. We'll tell you during compilation that there is an error that you have to fix. Up to version 1.3.3, the only marshalling schema that was supported by Cloudflow was Avro. I will talk a little bit about the newest version that was released literally last week, and now it supports both Avro and protobufs. Cloudflow also has a console, and I will show you some action, some console in action. that gives you the basic information about the application. So about the example, we're using, for this presentation, I'm using a simple fraud detection example, which is based on the article that I'm referenced. And the implementation is based on the autoencoder model in Keras. For those of you that don't know what autoencoders are, it's at the first glance a very weird thing that is attempting to predict input based on the input itself. At the first glance, it doesn't really make a lot of sense, but if, for example, if you're looking at fraud detection application, it does make sense because the assumption below this is that for the normal, not fraudulent transactions, the underlying model doesn't change, and every fraudulent transaction is going to have a bigger error. That's how we discriminate transactions between normal and fraudulent. So we will also talk about a couple of deployments. We've been talking about model serving as a service, and in this particular case, the implementation usually looks as follows. The input stream processing based on the Cloudflow for every element that comes in is invoking a model server to do the prediction. Because I'm using gRPC, I need to either use Ambassador, and the example that I'm going to show is using Ambassador, or I can use Istio to properly load balance gRPC. In the case of embedded model, the things are a little bit simpler because the model is running inside the stream processing application. And here I'm also showing the additional components that are necessary for the real deployment. We're not going to see them in code, but trust me, they do work. So when the new model is created, it is passed to the stream processing application, and stream processing application dynamically update the model that it keeps in memory. So let's look at some code so that it's not just me speaking. So if we take a look at IntelliJ, so this is the first thing that I was going to demonstrate. Every streamlet requires the schema definitions for, by the way, if you want to play with this, the project that I'm using right now is completely open. You're free to download it or clone it and play with it yourself. So first you create the model schema. Here I'm using Avro, and because I'm dealing with model serving, my model is TensorFlow. I also created a definition of the tensors in Avro. So this is surprisingly simple and straightforward. So once these things are done, you can actually build your simple streamlets. Let's look at some example of the simple streamlets. So the very simple one is this one, for example. So the streamlet is, in my case, a Scala class, but it can be a Java class itself, which extends Akka streamlet, and it defines the inputs and outputs. In this case, the streamlet doesn't have outputs, it just has a streamlet, and it defines a shape, and it defines the processing logic, which in this case is very, very simple. For the more complex things, in the interest of time, I'm not going to show you the code, but it's not so hard, believe me. So instead, let's look at a couple of other things. So one of the interesting things that I promised to you work is I can run the whole, the only other thing that I need to show you here is the blueprint itself that basically defines the main classes for implementation of every streamlet and connectivity between streamlets. So that is as simple as this. So if we want to run this locally, I just do run local, and it will hopefully build everything. And in a second, it will tell me that it's running. So, yeah. Every time when you trying to show off, it doesn't work. So let's try again very quickly. And if it won't work, it tells me that everything is running, and this is the file with the results. So if I want to see what's going on, I just go here, apologize for smaller font, and I do something like this. And you will see the results of my processing. So now I can kill it, and I can go here, and you will see everything that I'm printing out. So this is using the embedded model. In addition to this, what I've done is I've deployed my Seldon integration. I have a server running on GCP, and those are all the things deployed there. And now I can look at the console, and I can see everything that is deployed. I can go to different namespaces, see what's running in particular namespace. There is nothing earth-shattering here, but it's quite convenient. What is by far more convenient is this thing. So here I see the topology of my deployment. I know that this is the data generator. This is the model serving, and you can see that I've scaled it up. I'm using 10 of them. This is the decider that is looking at the error and decide based on the error which way to send the message. I can also, for example, increase the load on my model. So I can say that instead of 2 ingresses, I want to run 3. And after a while, it it will show that there are 3 of these, and this will start growing. While it is trying to grow, let's look at yet another thing. So if you look at the project, you can also see the model itself. Here I'm using Jupyter from the Cloudflow server that I'm also running in GKE. And in the project, there is the full code for this. If you're going to look at this, there is another interesting thing here, because I was trying to experiment with Shapley to see if I can do explanations, and it works quite nicely. So if we go back here, we see that now we have more data coming in, and we also see that the next streamlet is picking up this data, and it's a very handy tool to watch what's going on in your system. Let's continue here. As I said, last week, we released Cloudflow 2.0, which had protobuf support, which also adds Akka cluster support, which means that if you are running Akka Streams application, you can have persistence through Akka cluster. It introduced multi-image support for different runtimes. This was our problem in the beginning. Up to this version, Flink and Spark and Akka Streams were in the single image that was caused the jar hell to happen very often. It also changed Blueprint to explicitly connect streamlets to topics and configure topics, which opens us up to the integration with the existing Kafka clusters in the enterprise, and a new installer is there, and everything is completely open sourced. So Cloudflow provides great platform for MLOps, allowing deployment and stream-based inference. It can be used to support both embedded and service-based models. And there are some recommendations on when to use which. And also Shameless Plug, we just finished the book Cubeflow for Machine Learning, and is going to be available in November on Amazon. But if you have access to Aurelia learning platform, you can start reading it right now and give us any feedback. That's all that I have. I'm a little bit over time, but I hope this is okay. So let's see if there are any questions. Let me switch to the right screen. Yep. Of course, I can share the PowerPoint, but my understanding, everything is recorded, and you should get the videos from the organizers. Servlet can stream from Kafka topic. Is this a statement or the question? Can you rephrase the question? Because I don't think I'm getting the gist of it. How do we enforce the schema? We don't allow connectivity if the schemas don't match. If you remember, here I was showing you the blueprint. So the blueprint is saying this thing connects to this thing, right? So one of the things that I can do is I can say validate, no, verify blueprint. And what it will do is it will make sure something bad is happening with my machine. So during the verify blueprint, what is going to happen is it will make sure, because it knows what the schema is for this output and what the schema is for this input. It will make sure that the schemas are identical, and there are very simple ways of verifying identity of the schemas in both Avro and Protobuf. So to answer again the question, I don't check the topic. I check the producer of the data, and I check the consumer of the data, and I make sure that their schema definitions are identical. The same way, basically, that you do in the case of gRPC. You define schema first, and then you generate both consumer and producer to use the same schema. The same approach is applied here, but over streaming media. Yes, we do deal with Kafka consumer groups. This allows us scaling. If you remember, I was showing how I can do scaling, because in the case of Akka streams, those are effectively individual listeners, but the fact that they are the same streamlet automatically puts them in the same consumer group. I can override this behavior if I want to broadcast, but the default behavior, every copy of the same streamlet is running in the same consumer group. Cloudflow supports Spark, Flink, and Akka Streams runtime. That's correct. And when we're talking about Spark, I want to be even more precise. We support Spark structured streaming only, because this is about streaming, and we were going back and forth thinking about Spark streaming, but because Spark structured streaming is considered to be future, we decided to support only this. Again, it's open source project. If somebody has an idea to support additional runtimes, we will welcome your input. We've been looking a couple of times on Kafka streams, but we are, at the end of the day, commercial company. We just open source this project relatively recently, about 6 months. At the time when it was a closed project, we didn't have any customers for Kafka streaming. But again, it's open source project. We are more than eager to take anybody's contribution. Yes, Abdul, that's correct. Part of the problem that was always bugging me is I am a big fan of Cloudflow, And if you look at the Cloudflow, they abruptly drop the ball at the point of creation of the application where the model that they produce and expose can be used. And this is where Cloudflow, too many clouds, steps in and try to fill the void. So the main idea is, okay, great, you have the best model in the world. How do you put it in the production, and how do you put it in production in a streaming application? That's exactly the point that we're trying to make. And yes, you are absolutely correct. Without downtime is important thing, because when you're talking about streaming application, the downtime is no. That's a very good question, and it's an interesting question, because we had this problem recently when one of the companies came to us saying, okay, guys, you keep talking about streaming, but we really want to do model serving in the batch applications. And what are you going to recommend? And my immediate reaction was, what's your biggest pain point in the batch processing? And surprisingly enough, the answer was, well, it works, but it's slow. And here is the interesting thing. Even if you do batch, sometimes it's advantageous to for scaling it up to write it as a stream, where you have the producer that reads your batch file and converts it into stream. And because you can load balance on Kafka easily, you can improve performance significantly. We did a study for Selden a couple of months ago, and you can go to the Lightbend site. There is a blog that I've written. We took the Selden implementation that is doing individual serving in about 2 seconds. And by scaling it properly, we were running about 100 milliseconds for throughput. So even if you have batch, sometimes for proper scaling, you might want to use streaming approach, because it's by far easier to scale. I realize that I'm standing between you and TOD, and thank you very much for your attention. You've been great. Thanks again for coming to the presentation.